It's perfect.
So thank you for the introduction once more. So I'm Barbara Piętka and I'm working now at the University of Warsaw in Poland. And first, thank you for this kind invitation here. And I'm really happy that I can share with you our understanding of what happened in exciton-polaritons and how we control the exciton-polariton spin using real magnetic field and artificial magnetic field. So the problem that I will discuss today is simple planar microcavity when you can have two Bragg mirrors that are confining photonic modes inside. And usually we put some resonances in the center or in the maximum electric field distribution. And this can be most common of the excitons. So when you look at what happens with the photonic mode, so actually if you confine photonic mode in one direction in the and then in the reciprocal space, so in the dispersion, so energy and wave vector relation, it gives some parabolic dispersion. So actually, photon in such a cavity has some small but non-zero effective mass. And then the excitonic resonance actually also has some effective mass, but it is considered here as a flat resonance because we are really considering very narrow of wave vector around the minimum of the photonic mode. So the seminar today will be about the exciton-polaritons mode and about the photons and excitons itself also. Because in the strong coupling regime, so when you really have the strong interaction between excitonic resonances and cavity modes, we really have two new eigenstates on the system, which will be the lower polariton mode and the upper polariton mode in the cavity. So the lower polariton and upper polariton mode, they are composed of their original particles. So photon, it has some photonic fraction and excitonic fraction that you can, of course, tune by changing the respective position of the energy of one versus another. And then the coupling strength is usually given by is proportional to the exciton oscillator strength and the width of the cavity. So this is my basic system. So I built now exciton-polaritons composed from exciton and photons. But what I would like to decompose it in such a way that I would like first to consider what happens with the excitons. So to what actually external field are fragile excitons itself. And this is usually the external magnetic field and the Zeeman splitting that allows us to split the spin component of excitons. And then I will discuss what actually we can do with the photonic modes. So how we can tune the photonic modes to really achieve some control over spin of exciton-polariton itself. So this is the outline of my talk. So let's start first with the external magnetic field. So the real magnetic field that will act on our exciton-polaritons in the planar microcavity. So the excitons usually are composed, the excitons that couple to light, they usually are composed of two angular momentum, so plus or minus one or plus minus one. And they both, each of these components couples separately to photons of sigma minus and sigma plus polarization. So in this way, we have really two subsystems coupled separately. So if we apply external magnetic field, so what happened with the exciton energy? Actually, it has two terms that a magnetic field modifies. So there we have the diamagnetic shift that is proportional to the external magnetic field square, and then we have the Zeeman splitting. And of course, if you know that as the Rabi energy, so the coupling strength between exciton and photon is proportional to the exciton oscillator strength. So in external magnetic field, this oscillator strength is modified. So and Rabi energy usually increases. So at external magnetic field, when we have, for example, zero magnetic field, we have two degenerate modes of sigma plus and sigma minus polarization. And this is a typical photoluminescence spectra of the semiconductor microcavity with exciton-polariton. So you can recognize here the emission from the lower polariton branch and upper polariton branch. And this is spectra taken at zero magnetic field. So now I will play a movie when I will turn on the magnetic field, and you will observe how the polariton branches are modified. Okay, so now I increase magnetic field, and you see that the excitonic level shifts up due to this diamagnetic term, and actually even up to 14 Tesla for gallium arsenide structure, you do not observe strong Zeeman splitting of the lower polariton mode, because the Zeeman splitting is very low. It's usually in the micro electronvolts range. So how to modify now the structure to really increase the Zeeman splitting, for example, of exciton-polaritons? So we came up with an idea that we can modify the exciton, the quantum well, and we can introduce some magnetic ions to the structure. So this our structure now it will be composed in such a way that we have non-magnetic mirrors. We place few quantum wells inside, but then the magnetic ions are introduced to the quantum well structure, only to the quantum well structure. And like this, we build the semimagnetic cavity polaritons, because the p-type valent band electrons and s-type conduction band electrons, they couple to they interact with the manganese localized electrons through the SPD exchange interaction, and this actually leads to a giant Zeeman splitting. So how now this affect the Zeeman splitting for exciton polaritons will look when we have this magnetic semimagnetic structure. So we still have the diamagnetic shift, but actually in the cadmium telluride sample, the diamagnetic shift is really, really low, but we have the giant Zeeman splitting that even for 4% of manganese, it can be as huge as 80 millielectronvolts. So this giant Zeeman splitting is really proportional to the concentration of manganese ions in the structure, and therefore to the magnetization of the system. And of course, exciton oscillator strength is also slightly modified. So now let me show you the photoluminescence spectra of the lower polariton branch and upper polariton branch now from the cadmium telluride microcavity with manganese ions inside. So this is the almost zero magnetic field spectrum. But now I will play a movie when I will turn on the magnetic field. And what you will see that already at a very, very small magnetic field, the lower polariton branch splits. So we have the sigma minus branch that shifts up and sigma plus branch that shifts down. Okay, so here you can trace how uncoupled exciton modes are split. And actually this is the very huge splitting that then transforms to the polariton splitting, and you can have two branches of spin down and spin up polariton completely split in energy. What I will use in my in the rest of my talk is such a notation for the spin down polaritons or a sigma minus photons. I will use the color blue, and for a spin up polaritons or sigma plus photons, I will use the red color. And this allows me to easily visualize how the degree of the circular polarization in the emission of the polariton look like on the dispersion. So and then also this image here is split into the halves. So on the left hand side you can see the sigma minus component, and on the right hand side you can see sigma plus component. So at zero magnetic field, usually the two branches are degenerate and equally populated. But what you observe, for example, at 4 Tesla, for this detuning is that the exciton has a huge splitting that transforms to the splitting of the lower polariton branch, and you can have two separate modes. So this is my main effect actually that allows me to control the spin of the polaritons through the external real magnetic field through this excitonic component. Okay, so let's leave now. Yes,
sorry, Professor, yeah, there is a question.
Yes.
Well, we can talk now.
Oh, thank you. This is very interesting. I want to ask you about the manganese effect on the quantum well. So is this just like you just randomly deposit the manganese, or is this like a very specific strategy that only works with quantum wells? Can you elaborate a little bit more on this?
No, so the whole semiconductor structure is made in the MB machine. So we are sort of doping. So we open the manganese chamber, and actually this is deposited, and this is sort of random. So sometimes maybe you can serve some clustering, but then this is then the technology that will develop. So it is as homogeneously distributed as possible within the single layer. So we do not observe, for example, any diffusion between the layers. Yes? So the really manganese is concentrated in the quantum wells.
So I should think about the manganese just changing the sigma plus and sigma minus states of the quantum well. That's all the manganese is doing. Or...
Yes, actually, so the whole what this manganese is doing is actually acting on the exciton component. Yes, so it really couples modifies the bands, so the s and p bands of the electrons. So that's why we do have this giant Zeeman effect.
Okay, but it's still, but the Rabi splitting. The Rabi splitting is still larger than the Zeeman splitting, right?
Yes.
Okay. Okay. Thank you.
Yeah.
There is another question from Francesca Maria Marchetti. You can talk now.
Hi, Barbara. Nice to see you again. I wanted to ask you how Landau level physics doesn't enter into the problem when you have a magnetic field, as that depends on the G factor of your material. And I thought, I don't know if this is gallium arsenide. How can you avoid that?
Yes, because we do not have any doping here. So we assume that we really do not have free electrons and free holes. Yes, so that's why we for excitons, we are considering mostly this diamagnetic shift. And that's why we do not have these proper Landau levels that describe for the free electrons and free holes. So if we include the binding of the electron and hole into an exciton, so that's why the better description for the bound particle is this diamagnetic term.
Okay, thanks.
So you can continue now. Thank you.
Thank you. Okay, so I will jump now to the photonic modes. So what we can do with the photonic modes, so how we can control the spin properties of the photonic modes, so actually the polarization of the photonic mode itself. So what we can do is actually we can build a photonic lattice. This is one approach, and we can also change the electric constant in the cavity. So as comes for the photonic lattice, so there are actually many beautiful work in the literature you can find that people create this exciton-polariton spin filter or realize synthetic magnetic field in a honeycomb lattice or even polariton topological insulator, when you can see the photonic modes that appears actually in this photonic gap of this lattice that are spin polarized. But from my approach, we thought that it is very difficult actually to grow such a beautiful lattice, and we really concentrated more on the planar structure. So what we can have from such a simple picture like a planar microcavity, and let's focus now only on the empty cavity. So we do not introduce yet excitons into the structure. So planar microcavity, empty microcavity, so only two mirrors. And actually, it appears that the propagation or the coupling of the modes, so the localization of the TE and the TM modes are not equivalent when we look for the higher angle. Yes, so for a k equal to 0, these two for the zero emission angle or for the normal incidence, the two modes are degenerate. But as we start to increase the angle of incidence or the photon momentum, actually we observe the splitting of the two modes. And for example, I will refer to these modes as the horizontal and the vertical polarization, because I will just already put it in the frame of my laboratory. Of the axis of the laboratory. So I will point now in my further discussion all of the vectors of the polarization of the photonic mode in the Poincare sphere. So with this notation, I have this horizontal and vertical mode diagonal and the anti-diagonal mode, and sigma plus and sigma minus mode on the equator. So then you can see already that these this TE and TM modes are vertically polarized. And actually this leads to the many important effects already for the polaritons or for pure photons itself. So the photonic modes in the cavity, as you know, they are these two paraboloids. So if we plot it in the reciprocal space, so in the Kx and the Ky, so these are the two paraboloids now that they are split due to this horizontal vertical splitting. And now if you imagine such an experiment that you would like to transmit resonantly the laser through this mode, what was actually observed that for the linearly polarized laser, the photon that comes out from the cavity, they are circular polarized, and in this reciprocal space, so in the Kx, Ky momentum, so in the cross section for this paraboloid, they do demonstrate the very strong sigma plus and sigma polarization splitting, and coupled actually to a photons of the given momentum. So this was the first demonstration that the TE-TM splitting can lead to the so-called optical spin Hall effect. So the spin orbit coupling of the photons in the cavity. So it was demonstrated by Alexei Kavokin and in the theoretical paper. And what he really introduced that actually the effective magnetic field, so the synthetic Hamiltonian that can describe as the system, can be seen as an effective magnetic field or artificial magnetic field acting on the photons in plane on the cavity. So this quadruple time pattern was also observed in an experiment. So this is one of the first experimental realization for the lower polariton modes in gallium arsenide semimagnetic structure, in gallium arsenide semiconductor, of course not magnetic structure. And then there were lots of work that followed this approach, and then you can then many groups observe this optical spin Hall effect. But what will be for me the most important thing is really how these effective magnetic field look in the plane of the cavity. So my arrows now, they really do represent now the direction of the Poincare sphere. So what you can see here is that, for example, for k equal to 0, for a ky equal to 0, so we can have the vector pointing only in this direction. So really it has only sigma x component and do not have the sigma y component. So it will be like mostly in this direction of this S1 Stokes parameter component. So please note that actually this field, it do not has any component in the vertical direction. So there is no Z component, but this already allows to observe this nice quadruple pattern in the reciprocal space of purely polarized polariton or photonic modes. So this is my first synthetic field that was actually described many years ago. But what we can do next? Can we make a new step and a step forward? So actually what is proposed now that to this TE-TM splitting, we can add additional anisotropy. So if we add XY anisotropy in plane of the structure, so actually this will lead to additional splitting of the modes that were previously degenerate for the k equal to 0, for the 0 momentum, so for the 0 incidence angle. So, but now introducing the anisotropic material. So for example, the perovskites into the cavity, and the perovskites is characterized by ordinary and extraordinary refractive indices that differ actually of 0.15. So usually you can observe that these modes split, and this leads to the very interesting this conical intersection of the modes. So the next building block will be to add to this additional Zeeman splitting for the excitons. So now the system that was proposed here is that additionally to the TE-TM splitting, XY anisotropies, we add the Zeeman splitting. So this will be the Zeeman term added to the lower polariton mode. So this is the Hamiltonian derived for the lower polariton mode with the Zeeman splitting for for this lower polariton that acts on the excitonic component. And then we have the additional components here that actually this alpha describes the birefringence of the material, and beta here will describe the TE-TM splitting of the modes. And this actually evolved the whole picture into the very non-trivial photonic bands and photonic band engineering that actually demonstrate the non-zero Berry curvature that is actually very important and that quantifies the properties of the topological material. But what I would like to focus more is another type of spin-orbit coupling, which will be I will describe it for photons, but actually it was first described for electrons in the system that lacks inversion center, like for example, zinc blank and Wurtzit bulk semiconductors. So this is the Rashba and Dresselhaus spin-orbit coupling that couples a spin in the momentum for the Rashba term and for the Dresselhaus term. What I would like to simplify a little bit this approach, and let's put these terms of Rashba and Dresselhaus equal, and that's why it gives us actually the very simple Hamiltonian with here that depends, that splits us the circularly polarized mode only in one direction. So on the one direction, we have now two parabolas that are shifted in the momentum space. They are both there's one is sigma plus polarized, other is one is sigma plus polarized, other is sigma minus polarized. But in the perpendicular direction in the momentum space, this is a single parabola. So if you make, for example, a cross section at this level, you will observe two reciprocal circles, each polarized inversely. And here, for example, for this higher energy, the two circles will cross. So you have the two nice degenerate points. So I would like to describe you how we can actually make the spin orbit Rashba-Dresselhaus coupling inside a purely photonic structure. So what we did, we designed such a structure that is composed of two dielectric mirrors, and the distance between the mirrors is controlled by the silicon oxide spacers. So we can fix the distance, and it can be as small as 3.5 micrometers. So it can be the cavity that actually hosts multiple modes inside. But then what we do is we put into the cavity, we fill the cavity with the liquid crystal molecules. So the liquid crystal molecules can be considered as an elongated molecules, and we can align the molecules at the beginning initially by putting such an orienting polymer on both sides of the mirror. And like this, through the application of external electric field, so here we have the two ITO electrodes, and we can apply electric field, and then we can rotate the molecule with respect to the cavity plane. And this is the image of the cavity. You see that it is pretty bulky, but the support has to be really thick just to avoid the bending of the cavity, because we would like to be in the really planar cavity regime. So looking at the molecules, at the liquid crystal molecules, so we use the nematic liquid crystal that can be modeled actually by such an elongated molecule that has a different refractive index here in this two direction and different refractive index in this direction. So the two the ordinary refractive indices are the same, and then we have the extraordinary one bigger, but actually the birefringence of these molecules can be as high as 0.4. And then when we apply external electric field, we rotate the molecule versus the cavity plane, and this gives us the effective refractive index, for example, described by the angle of the molecule that is dependent on the external voltage applied to the structure. Okay. So this is how our cavity look like. So again, two mirrors, external voltage applied to the ITO electrodes, and elongated liquid crystal molecules inside. So what we do observe when we now, for example, perform the reflectance experiment, so what we see actually, it's nice photonic mode, and it is slightly here degenerate. So you can, when you probe the direction of the polarization, so here I will plot only the S1 component of the Poincare sphere, so the difference between the horizontal and the vertical polarization. So you see that we can have two polarized, linearly polarized modes. And now I will play a movie. When I will rotate, I will show you how when applying this voltage or decreasing this voltage, we really rotate the molecules with respect to the cavity plane. And like this, we can shift the modes one versus another. So we rotate the molecule, and as you see, this vertically polarized mode stays, but then the horizontal mode is shifted. And then by rotating molecules more and more, because we have the multi-mode cavity, we can come into resonance with the subsequent modes. So for example, when we look at this given mode, so this is the cross section for a normal incidence, we see that at the given rotation of the molecules, we have the two degenerate modes. And this corresponds actually to such realization when we have two modes of the same parity in the cavity, and so they have the same energy. But then, and we shift and we rotate the molecule, so we come into this very strange resonance that actually spectrum gets completely modified, and I will come to this later, but this is the regime when we have two modes of the different parity that become degenerate. And the third regime, when we have again modes of the same parity but of the different mode number, and now we have this the different splitting of the bands. So let me once more play this movie so you can see how the modes is shifting, and then there is additional mode coming. Now we have this peculiar regime when the two modes get split, and then we can even come with the third mode in resonance to this structure. Okay, so these are the three regimes that actually will be important for me in my further talk. So let's start first with this first regime. So we really have two modes of the same parity, the same mode number. So really this is a mostly typical example, as we know from the semiconductor structure, where we had the TE and TM mode splitting. So what we do observe when we make the resonant transmission of the linearly polarized light of the diagonal polarization through this mode, we do observe this quadruple pattern that actually demonstrate us this optical spin Hall effect acting on the pure photons. But the advantage of our structure that we can rotate the molecule is that we can now, when we induce some rotation of the molecule and we started to split the mode, so we add some additional term here. So we observe that this pattern, this polarization pattern, evolve into a funny shape, like something like a wheel. So what we did to understand a little bit what happens here, what we can do actually is not observe this resonant transmission in the reciprocal space, so in the kx and ky wave vector, but we can look in the real space, which is actually the Fourier transform of the reciprocal space. And in this real space, we do also observe this funny twisting of the polarization wave vector. And actually these patterns are known, this spin texture I widely investigated in the magnetic materials, and they are known as the half skyrmions on merons. So what we do have here actually is the lattice of the merons and antimerons in this polarization texture. So that was the image for when we transmit the resonant laser with the diagonal polarization. But now if we rotate the polarization and we go to the circular polarization basis, so actually what we do observe now, that now I played the movie when we smoothly change from the diagonal to circular polarization, and now you see that the two half skyrmion on the meron, they merge, and actually they evolve into the second order meron with such a spin texture revealed in this real space. So that was our simulation based on the Berman method, but that was also, we could also observe it experimentally and really confirm the existence of these second order merons in the pattern of S1 and S2 polarization in this regime of the TE and TM mode splitting. So in the sort of this standard regime of the as for the semiconductor cavity we know. So for the cavity field, with the liquid crystal, we were able to derive the Hamiltonian really to describe our system in the same sort of yes, including the birefringence of the material. So now delta is given by the birefringence of the material, and really now we can assign really this component and that component to this artificial magnetic field that was first proposed by Alexei Kavokin, that in plane of our structure acts on the photonic mode. And so this is what is for the NN regime. But then if we switch to the second regime, when we now put in resonance of the same parity, but for the n+2, so the second subsequent mode after the nth mode that we're probing. So then we do observe that actually we additionally put the term that describes as the splitting of the mode. So this will be the term that gives us the XY splitting of the mode. So that's why it's not zero for the zero-wave vector. And in one direction we can observe the mode crossing, and in the other direction it is different. So in this regime now, the effective, when we plot the synthetic magnetic field as we did for this optical spin Hall effect regime, so now we observe that this slightly different. So the widening number now it's not 2 like, for example, from 0. So just to retrieve the same polarization when we rotate the vector, so we have 1 and 2, but here and then we go the clockwise, the vector is rotating. So here is rotating anti-clockwise. So we have the winding number -2. So these two regimes are actually very similar, I would say. But in this regime, if you would ask me how then the meron on the Hubs fermion texture look like, so it is actually composed not of the merons, but of the anti-merons and anti-Hubs fermions. So what you do observe is, again, you have this lattice of the merons, and when we change from diagonal now to circular polarization, you see that this pattern evolve to the second order anti-meron for pure circular polarization. And these we could also confirm in our cavity for the S1 and S2 polarization. So they are now rotated.
We have a question from the audience.
Yes.
First of all, this XY, is it not KX and KY, or is this really imaging in real space, or is this like K space?
So this is now the real space. Okay, so this is the image in the K space, but then I can transform it onto the real space. So as we did, for example, for this previous regime. Maybe I will show you in the previous regime because I have the images. They are slightly better. Okay, so then you have the reciprocal regime, and then you have Kx, Ky vector, and then you produce this quadrupole pattern when you make the cross section. Yes, so this is clear. Yeah. And then if you make for example, either the Fourier transform of this image, either you really imagine the real space. So that, and in this way, you are creating this Hubs fermion lattice.
Okay, but then
because the fermions, they are defined. We did it because the fermions, the people defined it in the magnetic materials, but for the real space. Okay, so there was not sort of easy definition in the reciprocal space, because we have seen the quadruple pattern in the reciprocal space, and then we ask, okay, to what does it correspond? So, for example, here, yes, when we change from diagonal polarization to the circular polarization, we could only understand it when we actually made this imaging in the real space. So these are the experimental images. So here is the experiment, and here is the model in the real space.
Okay, well, great. Can I ask you also a question about, like, when you have these modes of the same parity but different modes? You say that induces an effective magnetic field. Can you go to that slide, please?
Yeah.
I think it was the next.
Okay, it was further on. Yeah.
Yeah.
Yep.
Okay. Okay. So clearly, you are not really having a real magnetic field here. So where does time reversal symmetry manifest? Like, if you shine light from the other side of the cavity, do you get the opposite?
No, so time reversal symmetry is here and not broken. So we do not really broke any symmetry. So our system is actually perfectly symmetry when we consider time reversal symmetry. So if you shine the light from one or from the other side, it's not a problem. So this is really not real field. This is like the synthetic field.
Sure. But then my question is like the time reversal symmetry should manifest if you shine light from the other side. Does the delta E become minus delta E in that case, or how does that manifest?
Yeah, but actually then the time reversal symmetry is a little bit different when you consider the real spin and then when you consider the polarization of the photons. Okay, so I do not have the slides here, but if you reverse it, and actually you need to reverse you need to make this invariance look for as they do look for a photons when then you make the when you reflect from the surface or you go from the other side.
Okay, but okay, and then the last question I would like to ask you is clearly the optical transition of the molecules in the liquid crystal are not playing any role here. So
No,
you're not really looking at polaritons. So
no, sometimes really we can see some emission from the molecules when we really excite very hardly with the laser, but no, now we just explore only the difference in the refractive indices in the different direction. Okay, so in this,
the optical transitions of the molecule are at what energy? So it's very off resonant?
Yes, it's off resonant, yes.
Okay, but there is no interest in really looking at the polaritons from the liquid crystal with those two modes?
Actually not. What we're mostly interested in, and I will show you later, we wanted to introduce to the liquid crystal cavity additional molecules that will really have stable excitons at room temperature, and then they will couple to polaritons. So this is what I have in few slides.
Okay, so just one last question. So what do you know? What is the what is the optical transition of the liquid crystal molecules in this case?
No, for this particular one, I don't know, but this is very far away in energy here. Okay. So we really, and it gives actually broad emission in a very broad spectral range.
Okay, thank you.
Okay, so we had these, and yeah, and then I had this regime, this very peculiar regime that actually was very interesting for us. So we really explored it a lot. For such a particular orientation of the molecules, what we do observe actually is the modes of the different parity, they become in resonance. And actually what we observe in the reflectance spectra is the separation of the two branches. And so with the minima for the different wave vectors. And then we could not probe, of course, the S1, we didn't S1 polarization or this S1 Stokes vector, but what we did actually is we plotted now the S3. So now I will show you once more the movie in the whole range of the tuning parameters, but for the S3 component. So now, okay, so let's rotate the molecule. So you see that actually the modes, they do shift, but then only now in exact resonance, the modes are purely circularly polarized. And then when you go far away from this particular resonance, you lose completely this S3 component for the of the polarization of the mode. So just having the ones look again. So then this mode will be sigma plus polarized, this will be sigma minus polarized. And actually there is here the exact crossing of the two modes for this at the resonance for k equal to 0. And then, so for this regime, we really could describe perfectly well this regime with this Rashba-Dresselhaus term known from the semiconductor structure with equal terms of the Rashba and Dresselhaus. But now this parameter alpha is actually fully described by the birefringence of our material. Yeah, so this is the mode numbers here. the mode number and the extraordinary refractive index and ordinary refractive index and the rotation of the molecules. Yes, so now if we plot how the synthetic magnetic field will look like, actually it will just gives us this sigma Z components. So these actually, the Rashba-Drasselhaus terms, so such Hamiltonian, we're also able to derive with our help of our colleagues, Professor Bardaszewski from our department, when you would take the waveguide approximation, so the Maxwell equation and KP model, and then we derive it around such a resonance, then you can have really demonstrate that this Hamiltonian corpus, then you can have also it from the Maxwell equation. So then you can find it in the supplementary information to this publication. Okay, so looking once more, having a look in this for the two paraboloid that actually shifted in this reciprocal space. So we have the sigma minus paraboloid, sigma plus. So and then when we make the resonant transmission in this reciprocal space, so you do really observe this nicely polarized circle that actually cross for high energy, and for low energy, when we low here, then you see the dots that corresponds to a different wave vector in the propagation. So as you actually ask what we can do further, so are we interested in putting some emitting material inside? And of course the answer is yes, because we wouldn't like only to probe the pure photonic mode, but we would like to modify it strongly with the excitonic resonance, is to have the all advantage of the excitons and the nonlinear interaction due to the excitonic component in the polariton state. So our first approach was to take some emitters, and the choice was a two-dimensional perovskite, hybrid organic inorganic, because actually they do show strong emission at room temperature, of course, because the whole system works at the room temperature. So the liquid crystal operation is mostly determined at room temperature. So that's why we needed strong emitter at room temperature with the energy that actually will match our design of the cavity. And they do have all the perovskites, they have the very huge binding energy, so they were actually like a perfect materials. So we deposited a two-dimensional perovskite layer on one of the mirror, where and then we designed the structure to have the maximum electromagnetic field distribution exactly at the position of the layer. And then we could tune the orientation of the liquid crystal molecule by the external electric field. So what we observed actually is, so this is the typical absorption and emission spectrum from our perovskite. So you see that in the regime when the absorption and emission, they do overlap. So these are the excitons that will couple to the photonic mode the most efficiently, because both absorption and emission processes are possible. So what we observe in this, so this is the photoluminescence experiment now, but to resolve better the modes, this left panel is resolved in horizontal polarization, this right panel in the vertical polarization, and then you see the nice anti-crossing, and then you can really feed the coupled oscillator model and find the Rabi energy for both vertical, horizontal, and vertically polarized mode, how does it couple. And perovskites, two-dimensional perovskites, also is the birefringent material. So from the ellipsometric measurements, we could guess what is, or we can estimate what will be the birefringence for our perovskite, and then we could model also this transmission for the modes. So this is the transmission derived from the Berman transfer matrix method, and actually it very well corresponds to this what we observe in the experiment. So this is now the regime when the horizontal and the very vertical modes are the eigenstate of our cavity, but then we can tune it to the regime where we been for this Rashba-Drasselhaus spin orbit coupling. So we rotate the molecules, and actually when you observe, when we approach this resonance, so maybe it's here not that perfectly visible because the resonance gets broader, but this is nicely visible when we plot already the S3 component, so the degree of the circular polarization. So what we observed is really we have two nicely splitted modes. then to model this now, so we first started with the Rashba-Dresselhaus Hamiltonian in the circular basis. So this describes as this eigenmodes of the system, and then we can add the excitonic resonances. So we couple now the exciton, each sigma plus and sigma minus exciton, we couple separately to each of the to the separate sigma plus and sigma minus photonic mode. So that's why we can expect actually 4 polariton branches with this anti-crossing here observed for the large wave vectors. What actually additionally we did, we were thinking of how the birefringence or the additional birefringence maybe of the perovskites or the liquid crystal will allow us to split the degeneracy point observed for the zero momentum. So if we will add some additional splitting here and the anti-diagonal term of this Rashba-Dresselhaus Hamiltonian, and then we couple it in the same way with the exciton branch, with the exciton mode, we can expect that actually we can have some splitting of this degenerate point now when we include this additional birefringence. And actually, this is what we observed in our cavity field with the liquid crystal and with the perovskites. That when I show you the photoluminescence spectrum now for the zero incidence, and then we observe this anti-crossing that really corresponds to this lifted degeneracy here at this minimum. And when we then model how the energy splitting will depend on the birefringence. So this is our model. When we increase this additional birefringence, we observed that actually this almost 17 millielectron volts will correspond to the birefringence below 0.2. So this is how we can now tune this modes and split the modes and somehow influence by additional birefringence to already birefringent material of the liquid crystal. Okay, so this brings me to the conclusion. So I would like to, I hope that I demonstrate you that we really do have lots of different tools to control the polarization of our polaritons or photonic modes through both exciton components and through the engineering of a different type of the synthetic Hamiltonian acting on the photonic modes. Yes, thank you for your attention. No, I wanted to, of course, thank you all of my collaborators. So special thanks I would like to address to Jacek Szczytko and Mateusz Król. So with Jacek, we are leading this whole group of the Polariton at the University of Warsaw, and we strongly collaborate with Witold Bardyszewski from the theory group, Maria Kamińska that helps us with the perovskite, and Tomek Stefaniuk with the ellipsometry. And we do have, I really appreciate our national and international collaboration with the Military University of Technology, that these samples with the liquid crystal are fabricated, and the discussion on the theoretical part and external magnetic field, and also with the Daniele Sanvito and his group for the further development of this perovskite material inside this liquid crystal cavity. So thank you very much.
Thank you very much for a great presentation, and we do have time for questions from the audience. You can either raise your hand, or you can also type them in the chat, and then I'll read them for Professor. There is a question from Professor Felix Dewin. You can talk now.
Hey, thanks a lot for the really interesting talk. It was very stimulating. Unfortunately, I'm a postdoc. That's still not yet a professor. Working on that though. Yes, you mentioned that you saw skyrmions, anti-skyrmions, merons, second-order merons, and I'm vaguely familiar with a skyrmion, so forget about a meron. Could you describe basically what these quasar particles are and what interests you about them?
So actually, we were just amazed by this funny polarization texture, yes, that we can have in the optical cavity. So in the pure photonic mode, we didn't know that we can expect that such a winding of the polarization. So from this, it was only for us interesting that we really can assign this rotation of the polarization, and then we can really make the resemblance of the real half skyrmions that appears in the magnetic materials. So, now what we would like to do in the future, so if we would like to extend this picture for this, make use of this strongly coupled system with the perovskite material, and then use the nonlinear effect, and then observe if we can influence somehow these merons and antimerons, and then if we can play further with them. Yes. So for the moment now, it was just the observation that actually it resembles the same picture.
Thank you, and I agree. The texture is very nice to look at. So thank you.
Thank you.
Yeah, so I'll give it a few seconds to see if there is any other question.
So if by any chance you have the idea what we can do and how we can play further on with these textures and with these merons and lattices, then we are very happy.
I'll let you know for sure.
Well, it seems like for the moment, at least, there is no more questions from the audience. So thank you very much again, Professor Barbara Piętka. And if you would allow me to share my screen,
yes,
a bit of final announcement.
Okay, thank you so much. Thank you for listening and for participating in this.
Thank you very much, of course. And I just want to remind the audience that next week we also have a Polarity and Chemistry webinar. This time we will feature Professor Levi Hung from Purdue University, who's going to talk about exciton and exciton-polariton transport imaged by ultrafast microscopy. So thank you very much, Professor, again. Thank you to the audience. I hope to see you all next week.